we can use the centroid of an area to determine the force resultant of a distributed load. So if we consider this triangular load, this line can have an equation of W by X on L. So at X equals 0, the load is 0, and at X equals L, the load is W. And if we cut out an infinitely thin rectangle, which has a width dx, and it's at a distance x from some origin, well, this differential force is equal to the height of this rectangle, which is Wx on L, multiplied by the thickness of the rectangle. And then integrating from x equals 0 to x equals L gives us the force resultant. So if we evaluate this integral, we get Wx squared on 2L, evaluated from 0 to L, and therefore the magnitude of the resultant force is equal to WL squared on 2L, or WL on 2. Now to determine x bar, where the force resultant acts, we evaluate this integral here. So we have x bar by our force resultant, which is WL on 2, is equal to the integral from 0 to L, and we have x being the moment arm, multiplied by the differential force, which is Wx on L dx. And now if you evaluate this integral, you'd have W on L, and we have x squared, that will be x cubed on 3. And we evaluate this from 0 to L. So that gives WL cubed on 3L, or WL squared on 3. And that's equal to x bar by WL on 2. And now if you solve for x bar by dividing through by W and dividing through by L, and then multiplying through by 2, we obtain x bar is 2/3 L. And that's expected that the resultant force acts at 2/3 of the length of this distributed load. And I'll leave it for you to do the same for this parabolic distribution. So that may have an equation of W by x squared on L squared. And you can find the force resultant and the centroid at which it acts. Please subscribe, like and comment to help me reach more students.